Hello, everyone.
Hello.
I haven't got through your test yet, so I don't know anything on that. Hopefully, I will be able to do those tonight or tomorrow. And they had to send me, of course, 2 questions, so I got to grade those. But I didn't even look at the grade book. Is it showing you the score that you made without that part, or is it just showing you like a clock or something in the grade book? Does anybody know?
It's the grade.
What's that it's showing?
Grade. I can see the grade.
Okay, cool. All right, I will check out the problems 4 and 10, and at least y'all got some sense of what you're doing right now. Cool. Oh yeah, that's right. You just had it had the right answer, but you had to show me your work. That's what it was. Okay. So I will. It's been so long since I made that test, I completely forgot everything. In fact, I went to class yesterday and thought I actually had not given the final yet, and I was all confused. I was like, "Oh my god, I don't know what's going on," but it's the wrong class. So, anyways, I hope everybody had a good break. Does anyone have any questions before we get started?
Yes, I had a quick question.
Of course, Sean.
In mastering physics, I just tried to look, but it's mastering physics isn't working for some reason right now.
Okay.
But there was a chapter 9 conceptual that's due this weekend.
Yeah, it's not supposed to even be in there because we haven't gone back to chapter 9 yet. And I'm trying to remember if we even go to 9. That might be
because I remember that from last semester, so I was just wondering if.
Yeah, that's not supposed to be in there at all.
Okay. Thank you.
So don't worry about that. I'll take that off and that sort of thing. Yeah, let me know anytime a chapter that you haven't been covering shows up, and I'll erase it. Sometimes when I copy them, I was playing around, experimenting with stuff for one class, but I was in another class, so I have those random assignments left over. I really shouldn't do that, but here I am.
Thank you.
Yeah, trust me. And if y'all ever see a case where I put a chapter that you weren't supposed to do, and I try to claim that as a grade, just let me know. And either I'll give you an option to make it extra credit, or I'll just erase it completely. So how about anyone else? Anyone have any cool electromagnetics material questions?
This isn't one of those type of questions, but have you heard any word on when the in-person teaching is going to start again?
I know for a fact that we're getting ready to do that in the fall semester. So we're in the process of trying to work out whether or not we can. Some of it depends on how many people are vaccinated, that sort of stuff. We don't know if we can require students to have vaccines before we allow them in, or show vaccination, or until we have a large percentage of the population, like 80% might be vaccinated. Once we reach that, then we could possibly just bank on the herd immunity. So I know that decision is still being labored about. As far as the summer goes, right now we're leaning toward, or at least my department, the physics department, is going with just as it is this semester, where we, basically can't have any meetings of classes, and that kind of stinks. It makes it, even harder summer.
All right, thank you.
No problem. If I know anything sooner than that, I will let you know. All right. Well, what I wanted to talk to you about was a little bit more of the Ampere's law. We learned a couple things last time. I had finished chapter 27, and I finished actually more or less everything of chapter 28. I just didn't do a lot of examples. So the 2 things we really learned, I'm going to write them down real quick, and then I'll show you the document cam, of course. But one of them was called the Biot-Savart law. I'll try to write it big so y'all can see it when I do actually put the document cam up. And the Biot-Savart law gives you a brute force way of calculating the magnetic field using a series integral. And that's what I'm writing right now. And it's series integral in that it's got a dl cross r hat over r squared, which I normally write as a dl cross r over r cubed. So that's one of them. The other one is Ampere's law. And again, I'm writing this down right now, and then I'll turn on my document cam. Ampere's law. And that basically says, well, I always cut it off for some reason. I'm just trying to click this thing. Turn back on. Okay. I go to hit the little arrow to the right of the camera, and inevitably it turns the whole thing off. So that's the law of Biot-Savart. It says there's a differential magnetic field element equal to mu zero times the current over 4 pi times dl cross r hat over r squared. But I use the r over r cubed. That way I don't have to think about trying to compute a r hat first. The main thing to understand is that the dl is a vector that ideally runs parallel to the current. So it runs along the path of the current carrying wire and points in the direction of conventional current flow. And the r, of course, points to the point at which you wish to know the magnetic field, and it points from, double checking this, and it points from the actual dl. So it points from dl to, I'll say P, script P, for which is the point at which you wish to know the magnetic field. Okay, Ampere's law is the closed integral of B dot dl is equal to mu zero times I enclosed. And remember, I is in general the integral of J dot dA, where J is the current density, which we've given you a formula for calculating, and you've seen some examples in your book as well as with me how you can calculate the current density. But it's made into a vector by making the magnitude of it equal to the magnitude of the amps per square meter and pointing in the direction of conventional charge, conventional current, dotted with the dA, which is a differential cross-sectional area element of the wire through which the current travels. So it could actually be this put into this slide. Okay, in most cases you just take the current, but in some cases you might have to do something like that, and I'll show you some examples of that today. I think last time all I had done was basically a current carrying or infinitely long wire I did with the law of Biot-Savart, and then I quickly did it with the law of Ampere. So I'm going to do some more Ampere's laws today, as well as some more Biot-Savart laws today. So let me start with another Biot-Savart law, and I will basically use the symmetries that allow for easy integration to do the law of Biot-Savart. That's really the only time you can do it. So what I'm going to do is imagine a configuration where basically you have a circle. That'll be radius little r, okay? And then that spreads out to a bigger circle of radius big R, okay? And what I'm going to do is I'm going to say the current is going this way around the system, okay? So you see the current's going like this, and what I would like to know is the magnetic field at that point right there, okay? So I'm going to start off by making this, let's say I make this the x-axis, and then I'll make this the y-axis, like so. And of course, given the right-hand rule, x cross j hat should give me k hat, so k hat points out of the page. Okay. So what I have to use is the law of Biot-Savart, and the law of Biot-Savart says B is equal to the integral of dB, which equals the integral of mu 0 I over 4 pi, all of which are constants that are going to come out in front of the integral, times dl cross r over r cubed. And remember, the dl is a vector along, differentially long, along the wire, and r is a vector that points from dl to r. So that was a mistake, remember, we made earlier. I was getting off by a negative, and then I realized, oh crap, I did the r pointing the opposite way. The r should always point from the current carrying segment of wire to the point in question. So let me start by trying to play out what's going on here by first looking at this. So I'm going to start by integrating from here all the way around. And that's actually why I chose the coordinates the way I did, because I already have a variable that goes in this direction. Okay. And I even have a unit vector, for instance, that goes in that direction. So that helps me. I'm going to call the R vector. It's going to actually equal negative R times R hat, which is a function of theta. Okay, so that R is actually, R hat is actually cosine theta I hat. That would actually get me, like if this is the angle theta, cosine theta would get me this little side, and then sine theta would get me that little side. So I'll say plus sine theta J hat. That's actually the definition of R hat as a function of theta. Okay, it's not the same as the R hat that we put up in here. This is the coordinate R hat. Okay, or a coordinate vector R hat. We also can say that DL, and notice this lowercase r means that's specifically for this part of the curve. When I get out here, it'll be the same thing, but with a big R. The DL is going to be, now I'll try to draw it big enough for you to see it, but small enough for it to still represent a differential line element. This little length right here is DL, and that DL should be equal to R d theta, and it points actually in the direction of increasing theta, which lo and behold happens to be a theta hat of theta as well. In polar coordinates, which is what we're dealing with, we're not dealing with a third dimension necessarily here. So I'm really just using like cylindrical coordinates here. Then this theta is just a function, this theta hat is just a function of theta. And in fact, if you take the derivative of R hat, d by d theta of R hat is actually equal to theta hat. And I think you can see that would be negative sine theta I hat plus cosine theta J hat. And that's really what it is. So I'm going to call L, DL, I'm going to say that is in fact lowercase r. I drew a big R there just to refer to any R in general, but basically it's whatever R you're dealing with. So remember, this is just basically that S equals R times theta formula that you know from trig. So DL is going to be, at least for this first part, so I'll put a little r here and put a colon showing you that I'm working for the stuff right here. This DL will be R d theta, theta hat. Okay, again, that theta hat turns out to be, you can also picture it this way. Theta hat is the direction this guy's in, and you can see the x component will be negative of the, if this is the theta, that's actually 90 plus theta, so it's negative of the sine of theta. I thought I'd turned this off already, but yet I have not. So negative sine theta I hat plus cosine theta J hat is what that theta hat vector is. Now I gotta move all this stuff because someone's moved my computer setup. It mainly was my mom playing probably Scrabble or something on the computer. So anyways, we now have that. And what I was saying is if you do a blow up of that R hat vector and theta hat vector, the R hat, you can see, relates by, notice this is the same R that points from the origin to out to here, R to out to here. I'm sort of doing this one, I guess. This would be the angle theta. And since this is X and this is Y, you can see that if that is 1 unit long, then cosine theta is equal to adjacent, which would be the X component. So R hat sub X over the hypotenuse, which is 1. So that's why I got R sub X, the R hat component, or the X hat component of R hat is cosine theta. And you can also see that if I take the sine of theta, I get the Y component of R hat, its magnitude divided by 1. So that's why that's the sine of theta. Now, if you recall that the theta hat is pointing in the direction of increasing theta, we know this is a 90-degree angle. So this right here is 90 minus theta, which means this is theta. Now, if you want to find the components there, again, theta hat's a 1 unit long vector. So this part right here is 1. This is theta hat. And you can see that if I take notice the sign is actually going to give me a number that points to the left. And therefore, I have to put a negative in front of it. And that'll give me the x component, which is why that negative sine theta is there. And then if I take the cosine of theta and multiply that by 1, then I get actually pointing upward, which is the correct positive direction. So that's why that's cosine theta, j hat. So that's really how all that crap worked out, even though you don't necessarily need it. I just wanted you to have some understanding why I'm doing what it is. And later in life, if you get into statics and actually specifically dynamics in your engineering classes, they'll be using this stuff, and they won't necessarily tell you that that's what they're using. But if you know this stuff, you'll find their equations are quite trivial. So now that we have all this stuff written down, I can go ahead and say, at least for the top part, so for the r hat component, I've got B, which I'll call top, is equal to mu 0 I over 4 pi. The r, of course, is a constant, so I can go ahead and pull that out of here. Well, let me go ahead and just work it out. I'll say the integral like this. Now I'm going to say dl. Well, our dl is r d theta theta hat, and then that's crossed with, of course, the r that points from here to here. That's why I said it was negative r hat. So I'll say cross with negative r times r hat. And that's also a function of theta over, in fact, clearly the distance is r. So this would be r cubed. So now you can see here's an r and here's an r. They're going to multiply to give me negative r squared. And then I'll divide that by r cubed and I'll get negative 1 over r. So I now have that this is equal to mu 0 I over 4 pi r times the integral of d theta. All that's left, though, is theta hat cross r hat. So I've got to go ahead and carry out that mathematics. You can see theta hat, which is 1 unit long, cross r hat, which is also 1 unit long, should have a magnitude of 1 times the cosine of the angle between them, which is 90. So that's 1 as well. Excuse me. Yeah, that's 1 as well. Oh, I said cosine. No wonder it's sine, because it's a cross product. Sine of 90, which is also 1. But it's actually pointing into the k direction, the negative k direction. So this negative that comes out from this one up here, that's ultimately going to be canceled out from this right here being negative k hat. Okay. So I can now say positive mu 0 I over 4 pi r k hat integral from theta equals 0, which is right there. This would be pi over 2, and this is, of course, is pi, so I'll say 0 to pi. And that's just the integral of d theta, which couldn't be any easier whatsoever. So I'm basically going to say this is mu 0 I over 4 pi r times pi times k hat. So you can see this pi is going to cancel out with that, and I'll get mu 0 I over 4 r k hat. So that's just the top part. Does anybody have any questions on that? Remember, this is a drawing that we're doing, and I just did the magnetic field due to this part. So this is what I call top. I'll call this 1, and I'll call this 3. This little segment and this little segment, okay? So now I got to do segment 1, which I think you can guess what it's going to be, but I still need to do it. So this one I'm going to underline because we know we're going to need it, because when it's all said and done, This is the magnetic field at the origin. I'm possibly going to get another magnetic field at the origin due to this little bit, and due to this little bit, and then another one due to this big bit, right? So I just add all those up vectorially, and that will give me the total magnetic field in here. So when I go to do part one, I see that DL is actually going to be this way, right? The current's going this way, so it'll be a negative dx I hat. So the differential length is dx, which is right along there, but it points in the negative I hat direction, so I put a negative in front of it and did d hat, or excuse me, did I hat. And then the R vector, which points from this thingamabob to the point in question, again, is that negative. In this case, is going to be a negative I hat, which you could also call it negative R hat, but you'd see for this special case, remember, R hat is a function of theta. When you put theta equal pi in R hat, you can see you're only going to get basically that. In other words, this is going to disappear. The cosine of pi, of course, is -1, and you'll just get negative I hat. So I'm going to do the same thing with that. I'm going to say it's points from here to there. So it's going to be in this case, in the positive I hat direction. So I'll say it is plus x I hat, like that. Okay. Now, this is actually the correct direction and everything, but the main thing is, you see, I'm going to have to take a cross product of DL and R hat, because that's what the formula says. It's DL cross R hat, but these two vectors are parallel, so that means DL cross R hat, or excuse me, cross R, is actually equal to 0, so the magnetic field due to this one is 0. So this whole segment contributes nothing. I'll go ahead and do 3 now as well. 3, the DL is this time going to be going the same direction. And in fact, it'll be the exact same thing. It'll be negative dx I hat. But in this case, the R is actually pointing from the DL, which would be having some value x over here, all the way to there. Again, that's the negative dx hat. Or excuse me, in this case, it's the negative x I hat. But again, DL cross R is just going to give me 0. So this means B sub 1 is equal to 0. And this means B sub 3 is equal to 0 vector as well. So this part and this part, which are radially pointing inward or outward, it doesn't matter. That they're going to give you 0. And that's sort of the rigmarole with using this Biot-Savart law. Is basically I would have to use a computer to do anything but a series of concentric partial circles and radial lines. So you can make all sorts of hubbub about all this stuff, but they're all going to be worked using these mechanisms, unless I teach you how to program a computer to do integrals, in which case, you know, you can do it then, but I'm not. And if you become a double E, you'll learn how to do that. Okay. Or if you become a physicist and work in this area, you'll do it. So I've got those. Now I'm just left with the bottom part. Okay. So now I'm going to do B for the bottom. That's going to equal mu 0 I over 4 pi times the integral. Now, if you'll notice, this is still the same stuff that was going on there. It's just further away. Instead of being a distance r from lowercase r from the origin, now it's a distance uppercase r from the origin. And that's your DL, which is equal to r d theta, still in the theta hat direction. Okay. And of course, your R hat, or excuse me, your R vector is still negative R hat, because it points from here to there. So it's got to be that negative R times R hat. That's the worst looking R I've ever seen, because there was going to be something else before. Okay, so I can put these in. I'm going to go ahead and say this will equal R d theta, theta hat, crossed with negative R d theta, R hat, over the distance will be R cubed in this time, and instead of integrating from 0 to pi, I'm going to integrate from pi to 2 pi. Okay. Now you can see again, the cross product is a linear operator, so that means I can actually pull out the d. That was not supposed to be d theta. I don't know why I wrote that in there. I don't know. I didn't write it above. Okay, no. So we're gonna pretend like this didn't happen. Ooh, I got a magic toy here. Hold on. Something big happening. It never was here. Okay, now it's been a jerk. Okay, so it worked for a second there. Anyways. So it's just negative big R times R hat. Again, I can pull this negative big R and this R d theta out in front of the cross product and let just theta hat cross with R hat. And again, theta hat cross with R hat gives me 1 unit pointing straight down. So that'll again be in the negative K hat direction. So now I've got negative mu 0 I over 4 pi R and then K hat. So notice the negative came from this right here, but now I also have a, well, I'll leave it like this. I took 2 steps. That's what's going on here. This is supposed to be a negative K. Let me put it that way, because the cross product theta hat cross R hat is equal to negative K hat. So this is where this came from. I think that's the clearest way to say it. So because of that, now I got a negative and a negative, which is a positive. So it's positive mu 0 I over 4 pi R K hat integral d theta. There was an integral here too. D theta from theta equals pi to 2 pi. So I think we can now see that that is mu 0 I times the integral of theta is just theta, 2 pi minus pi is just pi. So it'll be mu 0 I over 4 pi big R in the K hat direction. So again, the pi's cancel out, and I'm left with mu 0 I over 4 R K hat, and that's for the bottom. So the total magnetic field, I'm getting close enough where y'all can't see my paper anymore. The total magnetic field would be B top plus B bottom, and that's just going to be mu 0 I over 4 times, let's say 1 over R plus 1 over big R in the K hat direction. And that's our final answer. I think what you can sort of see, there's a little pattern. If you do some of these, you'll see there's a little pattern of what this integral becomes when the lines are circular concentric circles. They're basically going to be whatever fraction of the circle it has. Remember, a circle has 2 pi radians all the way around. So if it's going to be a whole circle, then it'll just be 2 pi all the way around. That's going to be multiplied by this top. But if it's a half a circle, then it's going to be pi. If it's a quarter circle, it's going to be pi over 2. If it's 3/4 of a circle, it'll be 3 pi over 2, so on and so forth. That's the real pattern. And then, of course, it's divided by the distance between the radius, or excuse me, the distance between the center of the circle and the circle, which is really just the radius. Okay. Any questions on that? like I said, this is the nastiest of the nasty, but once you get the hang of what's going on each time, I'm showing you all the gory details. If I was solving this problem for me for a test, like for the graduate record exam or something like that, I would immediately go from this step. I probably wouldn't even take the time to create the DL and the R vector. I would just jump straight from this step, and I'd use my right-hand rule to realize, okay, the current's going this way, so the magnetic field must be coming out of the ring. So I'm going to put it in the k-hat direction, and then I'm going to say, wait a second, that top half is only pi radians, so I'm going to multiply mu0 over 4 pi times pi, and then I'm going to divide it by the radius of that circle. So I wouldn't even do any of this stuff, and you should get to the point where you're not going to do any of this crap either, okay? It's nice to be able to do it because then you can explain it to other people, but at the end of the day, it should be, you should have enough practice to be able to do this over and over. And you'll see there's a lot of examples in the back of the book or at the end of the chapter that you can do. For instance, 34 is one where it goes through some arbitrary angle, just theta. And when you do like number 30, excuse me, I think I called it 31, it's 34. When you do problem 34, you can let me know what you get and I'll let you know if it's the right answer. But that's a general formula for any angle theta. So that's kind of nice. As long as the angle's in radians, it'll give you the general formula. 35 is another type problem. 36 is like this. 37 looks, well, almost looks exactly the same as this one. The only difference is 37. They called that R1. Excuse me. They called that R1 and that R2. So it's essentially the same problem as what we just worked. So you'll see that's the way you're supposed to do Biot-Savart laws, unless, like I said, unless you have a computer that you can program to do actual integrals. So anybody have any questions about how all this junk was done? That's it. All right. Now I just realized I ran out of paper. I'm going to grab another pad. Hold on, please. I thought I had some open already, but I do not. All right. So I'm going to now go back to my document cam, to my regular cam, my webcam, and talk to you. So that law of Biot-Savart, like I said, it's nasty. It looks horrible. It's got a cross product in the integral. That's got to be terrible. Blah, blah, blah. In fact, you can, just like I did with Ampere's law, I can use Ampere's law to derive Coulomb's law, or excuse me, I can use Gauss's law to derive Coulomb's law for electric fields. I can also use Coulomb's law for electric fields to derive Ampere's law. And it turns out when you do that, you actually get the right answer for what Ampere's law is. What the right answer for what Gauss's law is. Similarly, I can take the law of Biot-Savart and I can carry out that integral and come up with the equivalent of Ampere's law, or I can take Ampere's law and come up with the equivalent of the law of Biot-Savart. All of those are sort of interchangeable. That's really what's going on, but we're skipping the derivation between those parts. You wouldn't get to do that until you take like a junior or senior level electricity and magnetism course. And that, if you're an engineer as opposed to a physicist, that generally doesn't happen, like I said, till your junior or senior year in electrodynamics. So now let me show you another type of problem. Let's say we have a problem where you have two concentric wires. And this time I'm going to use Ampere's law. So let's imagine a wire like this that has an inner radius, let's call it little r. Okay. And then it's surrounded by a larger wire that's hollow. And that wire has a radius big R. Okay. But they're concentric cylindrical wires, so that's key to know. And I will call the outer radius of this cylindrical tubular wire, if you will. That's going to go on forever. That's going to be big R sub 2. So I've got little r, big R, and then big R sub 2 is what my, and I've noticed now that I'm not looking at the document cam, letting you see the document cam. So I just created a wire like this. And what I'm going to do is I am going to assume that it creates a current, total current I coming out this way. And in fact, a total current I is also going this way in the outer cylindrical tube, if you will. Okay. I will say this current is, let's say this current is uniformly distributed, because that's the sort of the next layer of complexity. The next layer after that is letting the current be, say, proportional to R, so that the farther you go out, you get larger and larger current. Or you could say it's proportional to 1 over R, stuff like that. So it gets a little more complicated. But I'm going to say these are uniform charge, uniform current densities. And that's called uniform J, or uniform current density, okay? So working that, I would like to calculate the magnetic field everywhere. So I want B everywhere. So what we do first is we imagine a Amperian loop that's concentric with the individual tubes, okay? So this is my Amperian loop. Just like before I had a Gaussian surface, now I have an Amperian loop. And I'm going to imagine, for instance, that let's say the x-axis is coming out of the page. So I'm going to draw, let me do a green, since I've been doing axes with green lately. I'm going to say the x-axis comes out of the page like this. I got it tilted just to show that it's 3D, but I can't, literally draw a vertical line like that. And then I'm going to have the y-axis that's in the page, and in that case it's vertical. And then I hat cross j hat gives me k hat. So the actual k direction, or the z direction, is this direction. So that's our coordinate system. X coming out, Y going up, Z going to that direction, okay? So according to Ampere's law, the closed integral of B dot dl is equal to mu 0 I. So the closed integral of B dotted with dl is equal to mu 0 I enclosed, okay? So what I'm going to do is integrate around this Amperian loop in this direction. In other words, out front it's going up, and then back behind the axis it's going down. So I drew that as a slightly lighter arrow. Okay. And this is out a radius, let's say a radius just plain X. Okay. So the Amperian loop has radius X, because I'd already used a little r for the inner things. I could have called it R1, R2, and R3, but I've already done it, so let's just stick with that. So this is lowercase r, uppercase R with no subscript, uppercase R with a subscript of 2. The radius of this Amperian loop is just plain X, okay? Now, what I have to do is take a hypothesis magnetic field. I'm going to hypothesize that for X less than R, B is equal to B of X in the, notice it's going around in that sort of same theta hat direction we talked about before, and that's theta hat of theta. Okay, and by putting the X in there, I'm saying I don't expect this magnitude to depend on anything but how far out you are from the symmetry axis of these two cylinders, okay? So that's what that's saying. My DL, of course, has to go around it, and my DL is not unlike the DL that I had from the law of Biot-Savart. The DL is going to be x d theta, and it's going to point also in the theta hat direction. Okay? So in other words, there's my DL, and that happens to be parallel to my B, my magnetic field. And that's the way this is supposed to work. Just like with Coulomb's law, we had a cross product with an area vector. In order for that to work, for us to solve for the thing inside the integral, we had to have the electric field vector to be everywhere parallel to the area vector, or completely perpendicular, or zero. Okay, anything other than that's going to screw this up and not let us pull this integral out of here. So this actually meets that criteria. It's got the B and the DL both pointing in the same direction. There's no other part, so I don't have to worry about those other parts that need to be perpendicular to it or need to have a zero magnitude. So now I can start off by writing, again, this is for R less than, or excuse me, for X less than R. I'm going to say that the left-hand side of the Ampere's law becomes the closed integral of B dot dl is equal to the closed integral of B of X theta hat dotted with X d theta theta hat. I can actually pull, remember the cross product and dot products are linear operators. So I can now say that this is integral B of X times d theta in the theta hat dot theta hat coming after it. Okay. Now we're actually integrating this along a surface of fixed X. So this B of X times X completely comes out in front, and I'll get X times B of X is equal to the integral of d theta, because theta hat dot theta hat is 1. Let me write that down in case someone don't know why later. That's actually 1 because each of them magnitude is 1 and the angle between them is 0. So cosine of 0 is 1. And this has to go from theta equals 0 all the way back around to 2 pi. So this is 0 to 2 pi. Oh, and this is times, not equals. So finally, I got 2 pi x times b of x, because the integral of d theta is just theta, and I evaluated it at 2 pi, and I evaluated it again at 0. 2 pi minus 0 gives me 2 pi, so I get 2 pi x b of x. Okay. Now this part is where, just like Gauss's law, this is the hardest part. Conceptually, it's hard to put this together, but mathematically, it's often hard to do the right-hand side. So the right-hand side of this is really mu 0 times I enclosed, which this time, since it's actually doing a distribution, I'm going to say mu 0 times the integral of dA dot dA. Okay, but for this, I'm going to say J points in the direction of conventional current, which is obviously in the K hat direction. So let's say J is equal to the total current I over the total area of that inner cylinder, which is pi r squared. Okay, but it has to point in the K hat direction. That makes it a vector. Okay. And then the dA part, now that's a little more confusing, but you could sort of take it as, since you want the actual variable that you're potentially integrating with respect to, which would be the x, since you want that to be a constant over one differential area element, what we would try is actual washers, if you will, sort of like washers, but not washers. It's more like rings. Let's call it rings. So that I'm going to say dA is actually going to be 2 pi r, or excuse me, 2 pi x dx. So dA is equal to 2 pi x times dx. Okay, and that of course also points in the K hat direction. Okay. So when I do that, I can say mu 0. The magnitude depends on pi r squared and I, which are no big deal. So I'm going to say I over pi r squared, which is really just our j, by the way, times the integral of k hat dotted with 2 pi x dx k hat. Okay. So I'm going to get mu 0 I over pi r squared times 2 pi times the integral of x dx. And notice here the k hat dot k hat just became 1 again. Now I'm going to integrate from x equals 0 to x because that's how far out the Amperian loop is. Okay? Because that's basically x is the distance away I wish to know the magnetic field. And like I said, it would have been better to use x, but here we are. So this becomes mu 0 I over, or 2 mu 0 I over r squared. Notice I put the 2 in there, and that came from the 2 pi that was here, and I canceled out the pi that was up here. So I got 2 mu 0 I over r squared times the integral of x dx. That's going to be 1/2 x squared. So I'm going to say that's 1/2 x squared, which when I evaluated x is 1/2 x squared. When I evaluated 0, it's just 0. So I now have this 2 canceling out with that 2, and that gives me mu 0 I x squared over r squared. Now you can look at this a couple different ways. If you multiplied pi by top and bottom, you get pi x squared, which is the area inside of there. And the pi r squared down here is the area outside. And you'd see that this is just j times the area of the current enclosed. So it's just a fraction, basically, of the total current enclosed. So when you're doing a uniform one, you can almost always find a simple fraction that will relate them. So you don't actually have to go through doing this integral. So the right-hand side ultimately becomes mu 0 I times x squared over r squared. So left-hand side equals right-hand side. That's our next step, just like we did in Gauss's law. And left-hand side, of course, we found was 2 pi x d of x. And the right-hand side we found was mu 0 I times x squared over r squared. Okay. You can see that one of these x's is going to cancel out. And I'll get basically b, which equals b of x in the k hat direction. Remember, that was our original hypothesis, in the theta hat direction. That was our original hypothesis for the actual magnetic field. So now all I got to do is solve for this b of x, which is mu 0 I over 2 pi r squared times x. So in fact, what we're seeing here is that this is just a linear function. The magnetic field increases linearly as you get farther and farther from the center of the cylinder. So the magnetic field increases linearly from 0 out to r. Now I'm going to try, that's part 1. So this is for x less than r. So now I'll do for x between r and big R. Okay, so the next step is doing the same thing that we did up there, but doing it for x in between r and big R. So this time our Gaussian, or excuse me, our Amperian loop is out here between the two, like in the space here. Okay. Everything else still works the same though, but we don't have to do that pesky J times dA because we now know the total current enclosed is just I. right? Because this is now completely encircling this current carrying wire. The total current coming from this current carrying wire was I, so I just have to do that. So now when I do this, I get left-hand side is equal to 2 pi. Now remember, this is basically the integral all the way around, so it'll be 2 pi x times b of x. And then the right-hand side, which is equal to mu 0 I enclosed, just becomes mu 0 I. And left-hand side equals right-hand side becomes 2 pi x b of x is equal to mu 0 I. And then, of course, that means b is equal to, again, it's b of x times theta hat. I can solve for b of x. That's going to be mu 0 I over 2 pi x. So this is for r less than x less than big R. Okay. If you'll notice, though, if you plug in x equal to r, then this will cancel out, and I'll just get mu 0 I over 2 pi x, if you will. And that's the exact same thing as this. So now I can add the fact that it's greater than or equal to r. So in other words, there's no discontinuity at b in going from r equals x to r equals something bigger than x. Now we got another case where we're going to do big R is less than x, but x is less than big R2. Now in this case, it's a little bit more confusing, but luckily the left-hand side is still easy breezy. We're still going to say, but in this case, of course, the circle is, the Amperian loop is out here. And we're integrating again that way. So you're still going to get b is equal to b of x theta hat, and dl is going to be x d theta theta hat. So we still have left-hand side is equal to closed integral b dot dl, which equals 2 pi x b of x, like that. Now the hard part on this one is the right-hand side, and the right-hand side gives us mu 0 I enclosed, which equals mu 0 I from the wire that we already did around. So I've got the current going through here, so that's mu 0 I. And notice that's consistent with the right-hand rule in which the direction I'm integrating. I'm integrating around this way, and if I put my thumb in the direction that I'm integrating around, my fingers point through the middle, which is the direction of the current. That means I get a positive current. If the current was going the other way, I would have to call that a negative current. So what I'm going to do now is I'll say it's mu 0 I minus mu 0 integral j dot dA. Okay, that's the difference. Because this outer one's going that way, that's inconsistent with my right-hand rule, which expects the current to go this way, so I have to make that current negative. That's probably the single most complicated thing about Ampere's law, but it's really not that bad. Now, J in this case, J is going to equal the total current I divided by the total area. Well, guess what? The total area is the cross-sectional area of this cylindrical shell. Notice that would be pi r2 squared minus pi r squared. So I'm going to say that's pi times r2 squared minus r squared. So that current is I over pi r2 squared minus r squared in the k hat direction. And that's just saying it's a uniform current density. total current divided by total area, cross-sectional area, should be the current density. The dA is going to be the exact same thing. It's going to be 2 pi x dx in the k hat direction. So I can now say that the right-hand side is going, or let's go ahead and just calculate this integral of j dot dA. So the integral of j dot dA, everybody can see that, right? That's going to become pi over pi, or excuse me, I said pi and actually wrote pi, but I was trying to say I over pi times R2 squared minus R squared. Whoa. Couldn't have made that worse. So R2 squared minus R squared. Every time I write this thing, I get a bad one. At least that one looks clear, so you can use that to read this one, and you can use this one to read that one. Times the integral of, now remember that's k hat dot 2 pi x dx k hat. Those k hats are going to give you a product of 1. So I get the integral of 2 pi x. And of course, that's going to be 1/2 x squared. So I now have 2 pi I over pi R2 squared minus R squared times 1/2. Now, in this case, you're taking it from x equals R1, or excuse me, x equals R to x equals X. So I'm going to say R squared minus X squared. That's the range of integration because I'm not going all the way outside of R2 yet. So this is getting really ugly, but it's like I said, this is sort of next to the worst case scenario. Okay. So now with that in mind, I can now say the right-hand side is mu 0 I minus mu 0 times, notice the 2 stays up there, but it cancels out with this 2. The pi cancels out. So I'm ultimately just going to get R squared minus X squared times I over R2 squared minus R squared. That's in the bottom. The pi's cancel out. And of course, that's it. That's the fraction of the current. And of course, that does make sense if you actually want to. I'll show you. Well, let me save that, and I'll show you a way you can avoid doing this j.da when we're all done. But right now, just notice that's a nice little ratio in front of I. So it's a fraction of the total current. That's the key thing. Now, if I really wanted to make that a little easier, so it's one giant expression, I could say equals mu 0 times, now I'll do R2 squared minus R squared. So what I'm doing is getting a common denominator for this I term. I'll pull out the I in both of them, so I got mu 0 I, but this one's got to be, since I want to add it with this, it's got to have a denominator and numerator, since it should be just 1, equal to the same thing. So I'll say all of this is going to be over R2 squared minus R squared. And then, of course, minus, and remember, fraction bars are parentheses, so this minus has to hit that R squared, and it has to hit that negative X squared. So I'll say minus R squared plus X squared. So the right-hand side is finally, quite beautifully, the R's cancel out. Excuse me, this was minus R squared. So that didn't cancel out. That's negative 2R. Okay, gotcha. So this is going to be R2 squared minus 2R squared. I did do R squared minus R squared. Yeah, minus 2R squared plus X squared over R2 squared minus R squared like that. So that's our right-hand side. Now I can set my right-hand side equal to my left-hand side. I'm actually doing it in the opposite order that I just wrote it. I don't know why I wrote it that way, but there I am. So it's 2 pi x b of x is equal to mu 0 I times r2 squared minus 2r squared plus x squared over r2 squared minus r squared. So we get something that sort of means something. It's just not that beautiful. So b is going to be equal to mu 0 I over 2 pi x. So this looks just like the normal formula for Ampere's law or for the magnetic field around a current carrying wire, but it's multiplied by this fishy factor. So the fishy factor still has to be there. All of that in the theta hat of theta direction. And again, this is for x greater than big R, but smaller than big R2. But again, if you let x equal big R, then you'll see this becomes big R squared minus 2R squared. So it'd be negative 2R squared plus R squared would be just negative R squared. And this would be R squared minus R2 squared minus R squared. So this would just cancel out and you'd get basically the exact same thing as you got for the other region. So now I can add this underbar there as well. Any questions on that? So again, trying to let you see this. Let me let you see all this. I'll slowly progress it by so you can pause it when you're looking at the video if you want to. And then from that, we start off with this. And we've got this result. So we got one more region to go to. That region is for x greater than R2. Okay. If you'll notice, if x actually equals R2, you get R2 squared plus R2 squared, which is 2R2 squared minus 2R squared. So it's basically just a factor of 2 over R squared minus R squared. So those just cancel out and you get this. But because of something weird that's going to happen, you're going to see that we actually do not get an electric field, or excuse me, a magnetic field outside. So our final part will be for x greater than R2. Now we got our Amperian loop completely outside of the coaxial cable. The left-hand side, which really hasn't changed in this whole problem, the closed integral of b dot dl is equal to just 2 pi x times b of x. The right-hand side, however, which is mu 0 times I enclosed, since we're outside of the actual object, we have a total current I going this way, a total current I going that way. And of course, as we showed you earlier, that current going the other way had to be a negative current. So we end up getting 0 for that. And in fact, we find B equals 0 for x greater than big R2. Okay. And I was hoping we could see some way where letting x equal R2 would actually make everything cancel out and just get a 0, but I do not see that that comes into play here. It might just be because I'm not seeing it, so it's a big complicated formula. But if you let x equal R2, you got R2 squared plus R2 squared minus 2R squared, which, like I said, is 2 times R2 squared minus R squared. And that's the same thing as here, except without the factor of 2. So all that would cancel out and give us mu 0 I over pi x. But I guess it all has to come from that I equals 0, which is the big effect here. So the I does actually equal 0 in this case. So our actual end of the day nasty magnetic field, I can graph because I know somewhat how the behavior is. And I'm going to have X here, and I'm going to have B here, and I'll have lowercase r here, then uppercase R here, and then uppercase R2 here. And I know that it went to mu 0 I over 2 pi R right here. It was linear in that portion. Remember, we got mu 0 I over 2 pi R squared times X. That was the linear portion. Then when we did X between R and that actually became a 1 over X function. So at this point, I'm going to say it went right about here. This is mu 0 I over 2 pi times big R. So this is falling like 1 over, should have been a little bit more curved than that, sorry. So in this area, it's a slight dampening. And then over here, you can see this last bit that wasn't 0. The X is really the big thing here. And I've sort of got a bunch of crap with X squared under X. And that sort of makes it like a linear, but in this case, it's like a falling linear. So we end up getting, in fact, another not quite linear, but looks pretty close to linear thing down to here, which is, of course, 0. So that's what our magnetic field looks like in all those various areas. Again, that's sort of the next to the hardest possible Ampere's law problem I could give you. If I wanted to make it the absolute hardest, I could say that this J, instead of being a uniform charge density, I could have said the J is some constant times, say, R squared, or some constant over R squared, or something like that. I can't do 1 over R, though, because the X would be integrated out of the actual dA element. So I got to be careful about which ones I can choose. But if I chose to give you J as some constant times R or some constant times X, then I could make it a little more complicated. But that's really about as nasty as it can get. Now, just to show you what you can really do instead of having to worry about that integral of J dot dA, when I say J is uniform, what I mean is I over A1 is equal to I2 over A2. Or I could say I total over A total is equal to I2 over A2. So when I was doing, for instance, the whole thing, I had I over pi R squared, but I enclosed only out to a distance X that was less than R was I over pi X squared, right? So from that, I can see I enclosed is just going to equal X squared over R squared times I. Notice what I got when I did the actual current using J dot dA. I got I times X squared over I squared. I times X squared over I squared. I mean, over R squared. So when the current is uniform, you can just set the J's equal to each other, where one is the total J and the other one is the partial J that you're using. and use the appropriate variables in here, and then you can solve for I enclosed, and that saves you the problem of having to do these integrals like the integral of j dot dA. Any questions on that? Again, this is a lot more. I mean, I'm trying to show you all the steps so you understand what's going on. But until you do, I would say probably 10 Ampere's laws problems of varying degrees and geometries and shapes like that, I don't think you're probably going to understand how to do it the shorter way. But you need to, okay, because you don't want to waste all this time doing this much work. I'm showing you all the work so you can better understand it. And then I try to do, of course, quick ones like I did on parts B, C, D, and E of this problem. I quickly did them by just knowing that the B is the left-hand side is going to be the same every time and all that good stuff. So there's all that. There's all that. And then there's the plotting that I got, which was that. Okay. So still no questions? Okay, if we had I can't remember if I did a solenoid and a torus last time, but let me quickly do those in the quick way you're supposed to use Ampere's law, because we only got like 5 minutes in class. So the solenoid is basically a bunch of wire loops. So you can imagine the electromagnet you made in grade school where you wrap a wire around a nail. Well, if you pulled that nail out, what you would have is a bunch of wires in the shape of a solenoid. And basically a single current runs around that wire so that it goes in, say, here and comes out this other side. If I wish to calculate the magnetic field in there, then I'm going to use Ampere's law, which says B dot dl is equal to mu 0 I enclosed, like such. What I'm going to do is assume this thing is quite narrow. Its radius is small compared to its very, very, very long length. Because when we get to the edges, the magnetic field all in the center is going to be straight along this axis, because the current carrying wire, if I grab these wires where the current's going into the page, put my thumb into the page, you can see the current carrying wire is going to create a magnetic field that runs straight through the middle. It'll be fairly uniform as long as the solenoid is fairly narrow. In other words, its radius is kind of small compared to its length. But when you get near the edges, of course, all bets are off, because it's going to spiral out and look like the magnetic field for a bar magnet, right? So what I'm going to do now is take my Amperian loop, and I'm going to make my Amperian loop run right here like so. Okay? So the current, the Amperian loop is going to go this way, this way, this way, and this way. My magnetic field is just going to be this way, and my, of course, DL for this top part is just this way. So part 1, closed integral B dot dl, if I call this distance x, then closed integral, or the part of the integral just over 1, and it's technically not closed because I'm just doing 1 bar, is going to equal just b times x. B times the magnitude, because the DL is parallel to the B. When I do this part 2, I see B is perpendicular to DL. See, DL would point this way, so the integral of B dot dl is equal to 0. The magnetic field, of course, is pointing this way here. It's pointing this way here, but it's really, really weak. So there's nothing really to deal with it. Not only that, it's 0 right there, because this one has a magnetic field that's going this way, and next to it's going the opposite way. So they're going to cancel out. When I come out here, again, the magnetic field is going to be there, but it's going to be so weak compared to this concentrated one. So part 3 is going to have B is approximately equal to 0. So the closed integral B dot dl, or not closed integral, the integral B dot dl is just going to be equal to 0 again. Now the current enclosed is another part. So when I look at the right-hand side, the mu 0 I enclosed This loop has a distance x that it's covering. And basically there's, say, n turns in that x. Well, if the number of turns per unit length is little n, then I would say this is going to be equal to mu 0 I times n times x, where n is equal to the total number of turns in the solenoid divided by the total length of the solenoid. So if I set those two equal to each other, I get Bx is equal to mu 0 I n x. The x's cancel out, and I get B is equal to mu 0 n times I in the, let's say, I hat direction. That's it. Okay, you just got to remember n is defined to be the total number of turns divided by the total length of the solenoid. The torus is the same thing, except the torus is more like a donut in that it's got all these rings of wire on the outside that maybe represent this, and then it's got these wires on the inside that represent that. So these are, say, the wires going in, and then this way you end up having a magnetic field B that goes that way. So with this one, you're again going to get, if this is the radius r, say, I'm going to get left-hand side is equal to just B times 2 pi r. And then I'm going to get the right-hand side is equal to mu 0 times I enclosed. Well, that's just mu 0 times n times I, where n is the total number of turns in the in this torus. So setting those two equal to each other, I find that B is equal to mu 0 I over 2 pi r times n. That's for a torus. And this is for a solenoid. Okay, that's it. I've done every possible thing, or showed you just about every possible thing you can do with Ampere's law. I did not show you the neat thing that your textbook does. You can use it to prove that a magnetic field cannot be directional, unidirectional, and uniform unless a current is present. That means it can be uniform, but with changing direction, or same direction but changing magnitude. So I would definitely recommend you check that out, because that's a cool little simple derivation that you can do. But we're done with class for this evening. Next time we will jump into and likely finish 29. 29 is a pretty quick chapter. So I'm waiting. I will wait for the last person to leave. You all are free to go other than that. And I will see you next week.
Have a good weekend.
Have a good weekend.
Thank you, Professor. Have a good night.
You too, Sean. Have a good one. Benjamin, Dylan, Jacob, any of y'all have questions?
Yeah, I had a question.
Yes.
I see the practice test is up for 27, 28. When are we planning on doing that test?
Oh, that's probably going to be the beginning of next week. It'll be an online test.
Got
So
it.
I'm probably going to give you that next time.
Okay, I was just wondering because I had seen it like last week, and I was just wondering.
Yeah, I just wanted to always make sure it's up there well in advance. I'm leaning towards probably giving it to you guys Monday.
Got it. And will this note page be online by tomorrow?
Yeah, I'll definitely have it tomorrow, say by noon or so.
Okay, thank you.
All right, have a good one.
You too.
You're welcome. Benjamin, Dylan, looks like y'all might be gone. I will call it a day.